Well, it's a great pleasure for me to be back here. I was here only a few weeks ago, and I hope that the audience is different, to at least to some degree, from the one then, because the talk will be largely similar to the one I gave before. This is a subject which is new, by which I mean only about 4 years old, and it's where I think twistor theory should be going. Now, I can't assume, I'm afraid, that everybody here is familiar with twistor theory, so I'm afraid that a lot of the talk will be a very rapid rush through twistor theory. I should explain some of the initial motivations, and here we have, I'm not sure I got these things up right way up. Here we have a picture of what it's about. Twistor space originally refers to Minkowski space-time, and what I want to talk about will be how to generalize this to a general curved Lorentzian real space-time, as we need for general relativity. But the original picture is that we have, instead of thinking of points as being the fundamental objects, we think of points as secondary objects. Now, the motivation behind these ideas is very much a combination of ideas from relativity and ideas from quantum mechanics. The idea is that a point is represented, this space here, you can think of, at least initially, as the space of light rays in Minkowski space. And a point then, over here, will represent an entire null geodesic or null straight line in Minkowski space. And the point in Minkowski space, you think of all the light rays through it, will be a sphere. And the idea is that this sphere is naturally a Riemann sphere, so in other words, a complex one-dimensional space, and this means that we try to think of the whole space in some sense as complex. So what twistor theory initially tries to do is to bring together ideas from, basic ideas, both from quantum mechanics and from relativity. It's not initially an attempt to quantize gravity. Quantizing gravity is maybe what I'm going to mention in the very last slide. I show you ideas which might move in that direction, but primarily the aim is to do classical general relativity in this framework. Now, as I say, the motivating ideas come from quantum mechanics on the one hand, where you have this basic role for the Riemann sphere. For spin half particle, you can consider the superpositions of two, one up and spin down, if you like, and an arbitrary spin state is a combination of that, and then the ratio of those two give you a complex number, which you can think of as by stereographic projection, is a direction on the sphere. So I won't go into the geometry here, which is probably familiar to you, but the direction of spin is simply a projective one-dimensional complex space. Now, the other input is from relativity, where one thinks of the light rays through a point, and the celestial sphere. You imagine two observers going at rapidly speeds which differ from each other by a significant fraction of the speed of light. Then the picture of the sky that each has transformed from one to the other by a conformal map, which sends circles to circles. So you have this structure of a Riemann sphere again in a different guise. This time it's as a complex one-dimensional space. So those two ideas are somehow to be combined together to think of the point in Minkowski space as associated with a sphere. And you think of that here, as regards the light rays here, as the celestial sphere of that point. Now, the first, I'm not going to get my pictures upside down if I'm not careful. And I'm sorry to use this old-fashioned technology, but it's, I'm afraid it's a great nuisance to organizers of conferences. So especially thanks to them. But it's handy for me to be able to do this. Here we have a little bit more of what's going on, and the explicit relationship between the point and between these two spaces. Here is this. It turns out to be a subspace of a complex projective three space. So we have four complex coordinates. These are the Z0, Z1, Z2, and Z3, which are the components of a twistor. And the relationship between them and the Minkowski coordinates over here, x, y, z, and t, where the speed of light is taken to be 1, is given by this matrix equation. that equation there represents what I call incidence. Incidence is represented geometrically in the top picture as the twistor representing the light ray going through the point, and in the other as the point lying on the Riemann sphere. So that's the incidence relation. Now, in order for this point to be real, you need a condition, it's quite easy to see that, on the twistor coordinates, which is this Hermitian quadratic form. And so therefore, you have complex projective 3 space, but subject to this one real relationship, which is given by that at the bottom. Now, that tells us that we have basically an extension of the space representing the light rays, where that quadratic form is not 0, to a bigger space, which is in fact the complex projective 3 space of ratios of those z's. Now, the correspondence really should be thought of as to do with this more complete complex projective space. Now, and this is what I just said before, the two roles for the Riemann sphere suggest the idea is that couldn't we have a complex space, the whole space being complex space, and this being a complex subspace of the full space, and for that the whole space needs to be a complex manifold, so we need to extend it. You see, of course, the space of light rays is 5-dimensional, this means this is a 5-dimensional, real 5-dimensional subspace of this complex 3-dimensional space, in other words, a 6 real-dimensional space, and it divides it into 2 halves. That dividing into 2 halves was an important motivation underlying twistor theory, because one was trying to, I'll come back to this later, it's a generalization of the idea of the Riemann sphere being divided into 2 halves by the real equator, and this represents the splitting of functions into positive and negative frequency, which is a fundamental aspect of quantum field theory. So I'll come back to that later. It does, in fact, realize that in a way which took me a long time to realize. But that is the more general picture we have to describe. And moreover, we should think not just of the projective space, but we often find it useful to talk about the non-projective twistor space, in other words, the vector space from which the projective space comes. So now we have, therefore, a 4-dimensional vector space of twistors, and the rays through the origin, the complex rays through the origin, represent the points of this projective space. And we have the Hermitian form being a real submanifold of the space, which gives us that here. Now, I've indicated schematically here the twistors with right-handed and left-handed spin, because it turns out rather magically that this entire space, not just the space in the middle, the entire twistor space represents the physical massless particle, which incorporates, when we put it non-projective, both the energy momentum of the particle, but also the angular momentum of that particle. And it very neatly describes the entire space. So you get right-handed and left-handed photons, if you like, spinning. I'm still talking classically there. When I say a photon, I mean a classical massless particle, and I'll say more explicitly what that is, represents now by the entire space here, non-projectively. There is a phase freedom, which is the only thing which is not geometrically realized in terms of the physical objects over here. As a point which I've sort of glossed over here, there are also parts of this space as infinity which are represented naturally in this space too. I'll come back to that later, but this is the basic geometry. Now, what I'm going to talk about today is how to generalize twistor theory in a way which, after seeing it, is a very natural idea, but it didn't occur to me for decades, many decades, I should say. The idea is what I'm calling palatial twistor theory, and the idea basically came from a discussion with Michael Atiyah. The word palatial, I think, now has 2 meanings, because it originally had to do with Buckingham Palace, but I think it also refers to the pyramids in Mexico, which I shall come to shortly. But the idea is that you still have this kind of picture here, as I had before. Infinity now you've got two ends. Before you didn't have this end of it. This is the non-projector space, but we've got a point at that end as well. And it's the key thing which is different is that the space is non-commutative. So we are entering into the area of non-commutative geometry, which I may say, although I've heard about it for many, many years, I didn't touch it with a barge pole because it looked too scary to me. But I realize now I have to dive into this subject in a more serious way than I did before. So I shall say something about that, but for the moment, let me indicate why one seems to be driven in that direction. I'm still, as I say, doing classical space-time geometry, but one is borrowing many ideas from quantum mechanics. And the idea is to pay them back afterwards if we can do something about quantum gravity. I should say that the idea of quantum gravity was always something which seemed to me not quite the right thing to do, because quantum gravity suggests that you want to quantize gravity or quantize space-time. And that never seemed to me to be the right point of view, because quantum theory needs help. I mean, quantum theory as it stands is an inconsistent theory. It's not just incomplete, as I think Einstein and Schrödinger and various people said, but it's actually, as in fact Dirac clearly said, is a stepping stone to a better theory. And what one needs is a theory in which the measurement process is also part of the theory, whereas quantum mechanics just has two mutually inconsistent procedures. You do one and then you do the other. But we need to have something which brings them together, and it has seemed to me for a long time that the link between these two must be through gravity and through Einstein's general relativity, generalized maybe in some way. Okay, now this is just a more complete picture of twistors. Instead of thinking of the Zs as just four components, so they really, you can think of them as two spinners, two spinners, and I call them omega and pi. Pi because it has to do with the momentum. Pi times its complex conjugate is the momentum. And the omega, which is a letter often used for angular momentum, is the thing which, together with pi, gives you the angular momentum. So they are classically quite understandable entities. If you take a null twistor, when I say a null twistor, I want for that, which that quadratic form I wrote at the bottom before is 0, can be represented by a light ray. And that light ray, you can think of the meaning of pi and omega. Pi just points along the light ray itself. There's an additional phase factor, but basically points along the light ray. And the omega would be the null direction pointing at this light ray from the origin. So it depends on the origin, but this is the picture for a null twistor. Now, I want to be more explicit. Well, first of all, I suppose I should throw this at you, but I won't leave it for long. Unfortunately, for those people not familiar with this notation, most of the things I tend to do is using the two-spinner formalism. Basically, this means that your tensor indices become pairs of spinor indices, one primed and one unprimed. Tensor indices are four-dimensional, the spinor indices are two-dimensional, and you have a canonical translation, which is basically the one I was using a minute ago. The metric tensor splits into two spinors, one unprimed and one primed. The primed ones are complex conjugates of the unprimed ones, and the geometrical interpretation of a spinor with one index, psi, say, is, first of all, the null vector, which you get by multiplying by its complex conjugate. That null vector points into the future, but there is a phase which you lose by doing this. The phase can be thought of as represented by a flag plane. The flag plane we think of geometrically more precisely by taking this should be really two-dimensional, that section through the light cone, so think of it as the sphere. This is the sphere over here, and then this point on the sphere represents the direction, and then you have a tangent vector to the sphere which describes the phase. And so this gives you the spinor in a more complete form. There is still a sign ambiguity, which tells you that if you rotate so that the flag goes around once, you get to minus, and then you have to rotate again, and it becomes plus. So you have the sign ambiguity, but apart from that, this geometrical description is complete. Okay, now that, I hope these things are at least sufficiently familiar, or at least you can take on trust what I say. I shall only rapidly go through the formulae, I'm afraid. This is the incidence formula, as I had before, and now we write this in terms of the omegas and pi's as omega equals r times pi. R gives you the position vector, which is this orange thing here, and the two spinors, omega and pi, are the part of the twistor. the indices are arranged up and down primed in this form here. When you take the complex conjugate of a twistor, you have to swap them around, and then it becomes a dual object to this, so that the scalar product with its dual is natural object, and that is the quadratic form that we had before. So when it vanishes, that gives you a null twistor, which represents a light ray. When you change the origin, pi remains fixed, but the omega gets shifted in this very simple way. So that's what this picture is doing for you here. Now, to go a little further, and this is the physical representation, the momentum and angular momentum of a massless particle has a momentum which has to be a null vector. It has, zero component has to point into the has to be positive, so it points into the future. That's achieved automatically by the pi-bar relationship, this thing down here. But then you also have an angular momentum, which brings both the omegas and pi's together. The round brackets means symmetrization, and this is exactly the angular momentum. The general angular momentum for a massive particle, it has to satisfy not just that the momentum is pointing into the future, but in addition, this thing called the Pauli-Lubansky spin vector, which is this object here, the dual of the product of the p with the m thing, is necessarily proportional to the momentum. And this condition is a condition which is naturally imposed on an angular momentum system to give you a massless particle. And that's automatically satisfied by this equation down here, and you have automatically a very neat representation of the angular momentum and momentum for a massless particle, satisfying all these relationships in terms of the omega and the pi. The only thing is pi must not be zero, that's all. I should say that some of these ideas have found a lot of applications these days in high-energy physics, where you can consider particles to be effectively massless, and scattering processes are now, twistor theory has proved to be useful in that. I'm not going to talk about that at all. I'm going to talk about a completely orthogonal subject, which is general relativity, classical general relativity, basically. Okay, now something else, which was an old feature of twistor theory, but which didn't feature very much in modern things, although it's a nice picture to use, and it was the origin of twistor theory in a certain sense, which is an explanation also for the name twistor. You see, if you want to represent a non-null twistor, see if it's a null twistor, you can say, okay, light ray. But if it's up here, and forget now about the angular momentum and momentum, you can think in terms of its dual. So the z bar is a dual object, and therefore represented by a plane in this complex projective free space. And this is the plane, I've drawn it there. Z bar is thought of as a plane in this space. That plane will intersect this space Pn, which is the space of null twistors, in a see, remember this is a real hypersurface, so that's 5-dimensional in a 6 real-dimensional space. And here we have a complex 2-plane, in other words, a 4 real-dimensional space that intersects this in a 3-dimensional space. That 3-dimensional space is naturally a 3-ball. No, have I said this right? This is a 4-dimensional space, and this is it's a 3-sphere. So that's a 3-sphere, and the question is, how do we picture that? You see, notice that these now are light rays, so we have a 3-parameter family of light rays, in fact, a congruence of light rays to represent that point. And so I've sort of drawn this sketchily here. I have a whole lot of light rays in Minkowski space, which represent this point. And these have a particular structure. Well, that picture is a little crude. Let me use a better picture. I'm mentioning this specifically, not just for fun, but because it will feature in something I want to say later, rather surprisingly. I'm usually tempted to use this in popular talks where I say, oh, isn't it nice? You can see what a twistor looks like. But then you forget about it. Well, I'm going to try and remember it now. This is, you see, this is to be thought of a space section, one instant of time, of that congruence of light rays. So we have a congruence of light rays. Through any point, there is a light ray, and they twist around each other. So what is this? Well, this is a projective. You take the 3-sphere and project it stereographically into ordinary Euclidean 3 space, and this is this space you get. These are the Clifford parallels on that 3-sphere, in other words, the Hopf vibration. And what are they? Well, you see, these things fill space. There's just a whole lot of circles with one straight line being the one in the middle, filling the entire space. And through any point, there is a direction given by this arrow. And that direction you must think of as where the light ray is going. So you have that point, it'll zip off along the tangent to that circle. And the next moment, this whole configuration, rather remarkably, if it's down there, the next moment, it will be the same configuration up here. Well, that kind of disassembles itself and reassembles itself in a different way. So it's geometrically quite complicated. But nevertheless, that's what it is. And this picture is why it's called a twistor, because you can see it twists all over the place. OK, now, what about the angular momentum? You see, that also tells you about it. Remember that it's the angular momentum and the momentum which is defines the non-null twistor. And if you take your origin to be some point, I'm calling it Q here, then wherever that sits, the tangent, well, pi is always the same direction. That's the momentum direction given by this arrow, big arrow here. And omega is the direction of that other arrow here. So that is, in fact, the configuration which defines the momentum and angular momentum of a massless particle. I mean, most physicists probably don't know that, but this is what it really does look like. So it's actually there in the physics. OK, now that I shall need to come back to later, so rather surprisingly. Now, I haven't said too much about quantum mechanics yet. Now, quantum twistor theory, you might call this first quantized twistor theory. And it turns out that it's very simple. The twistor and its complex conjugate are canonical conjugates. So that if you're going to think of first quantized theory, the canonical conjugate is also the complex conjugate. So that means that the twistors commute among themselves, the conjugates commute among themselves, and the twistor and its complex conjugate have a canonical commutation relation. So a lot of it was if you start to do quantum mechanics, that was the idea, and so on. Now, it turns out that the expression for the momentum and angular momentum, you might say, is there a factor ordering problem? Well, because of these round brackets here, no, there is no factor ordering problem. The momentum and the angular momentum are uniquely, unambiguously defined, and the commutation rules that they naturally satisfy as generators of the Poincaré group are automatically obtained from this. So it's a lot simpler. You see, these equations look rather complicated here, and these look incredibly simple. So twistor theory does that for you automatically. It does more for you, though. The one thing that you do have to worry about the factor ordering is for the helicity. That's this thing S, which previously you saw as the relationship between the Pauli-Lubansky spin vector and the momentum. So it's telling you how much spin there is. And it turns out to be this polarized thing here, z bar plus z bar z. That comes out of the equations. That's not forced. So this is the helicity. OK. And now it's an operator. So if you want to try and do quantum mechanics of a massless particle, it's very straightforward. You say, well, we mirror what you do for ordinary Schrodinger. Oh, sorry, I dropped it. Thank you. For ordinary Schrodinger quantum mechanics. You might say, what is the wave function for a twistor? Well, the wave function, you say, well, you see, if you're doing ordinary quantum mechanics, you say, OK, you might want the position representation or the momentum representation. You can choose one or the other. If you choose position representation, the momentum becomes differentiation with respect to position. If you choose momentum representation, then whatever I said before, the other way around. Anyway, here you say you can either choose the Z description or the Z bar description. So that means your wave function should be just a function of one of them and not the other. Well, what does that mean? To be independent of Z bar, well, that means df by dz bar is naught. In other words, holomorphic. That's the Cauchy-Riemann equations. So you have a function which is naturally holomorphic. I should say that one of the big motivations behind twistor theory, which I hadn't emphasized up to this point, is holomorphicity. I'd always been struck by the power and the sort of combination of flexibility and rigidity that you get in complex analysis. And it struck me that, wouldn't it be wonderful if complex analysis, in some sense, lay at the basis of physics. And that is part of the motivation, I should say, behind the twistor approach. Try and keep everything holomorphic as long as you can. So this is very gratifying that somehow you have this holomorphic function arising naturally if you're trying to describe a wave function in Twistor terms. The helicity now, you see what that means. It's basically the Euler operator, zd by dz, but it's displaced in this way, -2 minus the Euler operator, and that is the helicity. And so that means you have a relationship. The Euler homogeneity operator, the eigenvalues of this operator are therefore homogeneous functions, and you're looking therefore for homogeneous functions of a degree given by this here. Let's see, n is the homogeneity degree where the, the homogeneity is -2 minus n, where I think n is equal to twice the spin over h bar. So it's n is an integer, and so you're looking at an integer homogeneity degree. So that's the idea. You could alternatively use the dual twistor description. That would be just equivalent, but everything's sort of the other way around. It's a helicity change. There is a chirality choice if you're saying use z's and not w's, w's being the z bars, if you like, if you want to consider them as a new variable or use a new letter. And so it's the choice of which handedness you'd make. But if there's a natural choice that nature makes, that may be, but that's not forced upon us as yet. Now, this tells us then that the wave function, the Twistor wave function for a massless particle of helicity n over 2, basically, is given by a homogeneous function of homogeneity degree -2 minus n, which is holomorphic. Now, what has that got to do with the real field equations? Well, that's the point. What are the real field equations, first of all? Well, these are the massless field equations in flat space for arbitrary spin. For s equals 0, you have the D'Alembert, the wave operator. For s positive, you have a symmetric spinner with primed indices, which satisfies this generalized Weil-Dirac equation. And if it's negative helicity, you have unprimed indices, which satisfy that. So these are the standard equations. I should perhaps emphasize that these are things that in ordinary tensor notation for spin 1 and 2 are well known. In case of spin 1, it's the Maxwell equations when you're looking at anti-self-dual and self-dual parts. So these all both satisfy the same equation. And if you're looking at linearized gravity, free gravity, spin 2, same case. This is the spinor version of that, where you're simply looking at the Weil spinor, as we were hearing about in the last lecture. The linearized Weil spinor, which has symmetries and so forth, given by symmetric spinor, subject to the very same equation that I just wrote down. And these things are conformally invariant as well, which I've got down at the bottom. Okay. Now, so we have these equations. If we're doing classical ordinary notation stuff, we have homogeneity degrees is given by this table at the bottom here. So these are the helicities here. So here's Maxwell case, this one and this one. Here's the linearized gravity case, that one and that one. And you see the homogeneity degrees if you use the Twistor description. Here's if you use the dual Twistor description. For the Maxwell field, you have, for the left-handed, 0 homogeneity. For right-handed, -4. For linearized gravity, it's +2 for the left-handed and -6 for the right-handed, which looks awfully lopsided. Indeed, it is lopsided. You get back the other way around if you go to the dual Twistor description, but somehow you have to make a choice. Okay. And then you get the wave equation in the middle, and you get the Dirac-Weil massless neutrino for this spin half case. -1 and -3 is the homogeneities. Okay, so what's the relationship between this and this? Well, the relationship is given in terms of a contour integral. I think I shall, yes, here we go. Again, it's quite remarkable the way it all works. These are all different spins, but let's take the wave equation first. That's simplest to describe. Then you have a Twistor function that's homogeneous at degree -2, which is holomorphic. And you holomorphic things, they're natural things to do contour integrals on. This is a form, one form, which is simply given by the pi's. It's of degree 2. the degree 2 cancels out the minus 2 over here, and so you get a degree 0 thing, and this is a natural thing, therefore, to do a contour integral in the projective space. Geometrically, it's nice to take a simple example. Here we have a simple example where you need some poles so that you can integrate them around them to get a non-zero answer. And that's what I've taken the simplest case, 2 linear functions giving us 2 poles. These give us planes in here where you have function as singularities. And then you've got to integrate around these planes. I think I want to make a point here, which I haven't done yet. You see, one's looking for wave functions. You can look at this classically perfectly well as well. You can think of this as just giving you classical solutions of Maxwell's equations or the linearized Einstein's equations. And that's fine. You can do that. But the motivation here was partly to do wave functions, which means thinking about positive frequency condition. Now, the positive frequency condition can be best understood in terms of complexifying and look at complex Minkowski points. Now, people talk about the forward tube. Now, the forward tube is the region of complex Minkowski space where the imaginary part of the position vector points into the past. Now, it's all very confusing because it's the past and it's the forward tube, but never mind. So you say that the imaginary part, this is where these arrows are, is pointing into the past. Now, if you have a complex point in complex Minkowski space is represented by a line. Remember that for a real point, it was a line, well, that was, you see, I put a Riemann sphere, but these lines really are Riemann spheres. They're projective lines. So this is a Riemann sphere. Sometimes I draw them as long sausages to make you think of them both as lines and points, as spheres at the same time. But think of that as a Riemann sphere. That projective line, if it lies entirely in Pn, that's a real point. If these are all the different possibilities for the different arrangements for the light rays, and I won't go into them all, but the main thing you were interested in is when the imaginary part points into the past, that is where the line lies entirely in the top half of twistor space. So the forward tube, the place where you want your complex wave function in its analytic extension to go to in order to represent positive frequency, which is what you want for a free particle, then you're talking about the top half of twistor space. So that is a point I just want to say here. The top half of twistor space corresponds to the forward tube, which means wave functions. OK, well, what do we have here then? We want something which extends not just for lines in Pn, which would be the real solutions, but where that line is allowed to drift up into the top half of twistor space. And then that means we want our contour integral still to work when that lies in the top half of twistor space. Now, that is fine here, because if your line, which is the intersection of the planes A and B, lies entirely in the bottom half, so long as it does, then these two planes never intersect in the top half, and that means your line, which represents the point about which there's this Riemann sphere, you see, is that line. And the singularities now where that intersect, A and B, those are the 2 points here and here. And so your contour simply separates the points from each other. It's well defined. You have a nice answer, and that gives you all the wave functions which are positive frequency. What's beautiful about this is you simply get them all free. You just say holomorphic in the top half of twistor space, and then there's this awkward thing about saying you've got to have separated regions of singularities. Now, I worried about that for a long time, because it was doing the sort of thing I wanted to, but what on earth does separated singularities in the top half mean? OK, you see, I've put them as great camel humps here, because you can smear these things. You can move them around and smear your singularities into bigger regions, and that's exactly what I've done here. But they mustn't intersect. As long as they remain separate, then you can do your contour integral, and then you get your answer. I should also mention that you can easily put the indices in by putting lots of pi's in here, and that gives you your index for the functions which are less than -2 homogeneity, so you need these pi's to bring it up to -2, and then this gets it up to 0. In the other case, and it's interesting to see, here you see an aspect of the twistor quantization coming in. Because you might say, OK, we know how to do that one. You know how to do the ones with the pi's in. How do you do the other one? And it wasn't obvious initially, but it was Lane Houston, really, who pointed this out initially. I don't know from this motivation or not. But the point was that when you take the complex conjugates, the pi's will all be pi bars. And what should pi bars be? Well, d by d omegas. That's the quantization rule. And then you put d omegas in here, and that gives you the other ones, the ones with the unprimed indices. So you have the whole lot. And what you really have to understand is what it means to have your function homogeneous and holomorphic outside a pair of camel humps. And this is also a bit of a stupid thing, because if you add lots and lots of them where the camel humps are in different places, as they will be, they'll get rotated around when you do Lorentz transformations. What does it all mean? Well, it took us a while to realize what it all means, and basically some input from Michael Atiyah was very important here. What one is really doing is sheaf cohomology. I should say that this initial thing, the idea is, how do you think of the camel humps? You don't think of the camel humps. What you think of is the space left behind by the camel humps, which of course is this region here where the function is meant to be holomorphic. And you think of that as being the intersection of two open sets, each one removing one camel hump. So there we are. There's the two camel humps taken out. And this is the intersection of two regions, each of which has one camel hump taken out. And the union, the union of the two regions is the whole space. So this is an example of finding a covering of PT plus by two open sets, this and this, whose intersection is where you define your twistor function. Two open sets, and there is the twistor function in the intersection. More generally, and this is how you can get around the special business of it all, you can think of a covering with lots and lots of open sets, and your twistor function is really a whole collection of functions which have to satisfy these normal cohomology relationships, which I won't go into if you're not familiar with them, but it's all there. And what you want to say is you consider this set of twistor functions modulo those which are defined on regions as a whole. And that's what the cohomology is relative to a covering, and then you take a refinement, and then you talk about Stein sets, and you say, it doesn't matter, you stop at a certain point, and so on and so on. But let's not worry about all the details of that. Is the net, and I should say also, you can do contour integrals by means of this branched contour procedures. But the net conclusion of all this is what we are really talking about is sheaf cohomology of the top half of twistor space. And now it's sort of mathematically very satisfying, because it was, remember I mentioned this motivation originally about splitting functions into positive and negative frequency by looking at the real part of the function along the equator there, and positive frequency goes one way and negative the other way, and I think normally it's the other way around from what I've drawn it, but never mind about that. And this is now an analog where it's the whole of twistor space, and instead of looking at functions, you're looking at first cohomology. And it's exactly the same picture. The first cohomology in the top half and the bottom half gives you positive and negative frequency splitting, which is very satisfying. OK, let me not say any more about that, except that it seemed to me once one had this picture, it all seemed really very natural. It's not only natural, but it generalizes. And it generalizes in these two ways, which I've indicated in this picture. The first one came second and the second one first, so let me call this one. This is my then graduate student, Richard Ward, who very quickly, after I had the general relativity case, generalized what I was saying to Yang-Mills fields. I'm only going to show you this very quickly because I'm not going to talk about it much here, but it was an important construction for particularly the way that twistor theory found applications in integrable systems and differential geometry and so on. But the idea was that you can describe Yang-Mills fields. Now, it's not just Maxwell fields, but fields which are nonlinear because you're looking at a non-abelian group and so on. And you have a covering of your twistor space, and then you're looking at bundles over there, and you construct bundles over the whole thing. And that is the construction. I'm not going to go into that. I'm going to talk more about the general relativity construction, which we think of as, OK, we had a cohomology element. In the case of spin 2, those were, well, -2 homogeneity degree functions, which are defined on the overlaps between open sets. Now, think of those functions as painted on the spaces. Now I'm going to allow the paint to dry, and as it dries, it crinkles the space up a bit. So you now have constructed a curved manifold. And that is really the idea. You can construct curved twistor spaces by crinkling up the twistor functions of degree, homogeneous degree -2. I give you the general idea here, going back to, first of all, flat space. You remember that a point in the manifold, which is now complexified Minkowski space, represents a line in the complex projective 3 space. When they intersect, that corresponds to points being null separated over here. Now, what I'm going to do is to curve up the twistor space in the sort of way I was describing. Let's just think of 2 sets. And I'm also going to think of it locally. Locally in the space-time, which means take a line in twistor space and look at the tubular neighborhood of that line. Now, I'm going to deform that by chopping it into 2 pieces. Well, here I have 2 overlapping pieces. Remember, that line represents a Riemann sphere. So this is a Riemann sphere cut into 2 hemispheres which overlap here. Now I'm going to shift them on the overlap. So now I just shift one along with the other. That's where the vector field is. I have to exponentiate that vector field, or that function which gives us a vector field. I'll come into that in a bit more in a minute. I shift one with respect to the other. And now that line is no good. You see it's split in 2. There's a nice theorem due to Kodara which tells us that we can actually, if as long as this is a reasonably small deformation, a finite but not too big deformation, then you can find, not only can you find new holomorphic curves, but these lines, which were a 4-parameter family initially, remain a 4-parameter family. And since it's a 4-parameter family, the points representing them will be a 4-dimensional space, a complex space, and you know what null separation is because it's the same as over here. And then this space, therefore, has a complex conformal structure. Therefore, it has a Weil tensor defined, and so on. And you then have a general anti-self dual complex space-time. If you wanted to satisfy the Einstein equations, it's quite simple. You want this projection to the pi space to be global. I want to say that in a slightly different way now. Let me move that over here. In fact, before doing that, I need to say something about infinity twistors. You see, the representation of Minkowski space I gave you was actually completely conformal. It doesn't say anything about the metric. The analog of the metric is this thing called the infinity twistor. Now, when you don't have a cosmological constant, it's a skew-symmetrical, simple, in other words, degenerate skew object. When you do have a cosmological constant, you have a term here. You see, that would go to 0, and so it's a degenerate object. But if, that is to say, it's degenerate in the sense that the determinant is 0. But in general, where there is a cosmological constant, it's non-degenerate. And so you have these things which are called the infinity twistor. They give you the metric. They also tell you where infinity is. So it's a useful thing. But it gives you de Sitter space as well as flat space. And the contraction of I with its dual, the duals are given by here, it gives you lambda, the cosmological constant. OK, so that's the idea of the infinity twistor. Now, a way then of representing the piecing together of twistor space, you have a vector field, which is very simply defined in terms of the infinity twistor. You can do it with omegas and pi's this way if you like. But let's do it with the infinity twistor, because this allows you to talk about a non-zero cosmological constant. This was carried out in detail by Richard Ward. He showed how the construction worked in the case of a non-zero cosmological constant. You just make sure that this infinity twistor has a lambda in it if you like. But whichever way you have it, this deformation is an infinitesimal deformation of one patch of the other. Then you exponentiate that to make it a finite deformation, and then that gives you your construction. OK, so that's fine. All that worked very nicely. But this was the problem. And the problem has been sitting there for, I would say, 40 years or so. I'm not sure. I have stopped counting. It's what we call the Googly Problem. And those of you who know about cricket will know what a googly is. Those of you who don't know about cricket, which is probably the majority here, a googly is a cricket ball which is bowled. I should say what a leg break is first. A leg break is a left-handed spinning ball. The ball is bowled in such a way that it spins left-handed. And the thing is that a person who can bowl a googly, it's a very clever thing to do. It looks as though the chap has spun it left-handed and it spins right-handed. It's a very clever thing to do, and that's exactly what we want to do. In that framework, which spins naturally left-handed, you want to do a right-handed. So we call it the Googly Problem. And this Googly Problem is even more difficult in twistor theory, I think, than it is in cricket, to try and find how to do it. So that's really exactly what we were trying to do. How do you have a formalism which incorporates both the right-handed and left-handed parts? And if you want to do classical general relativity, you've jolly well got to do that. So here was the initial idea. I was trying to think, how on earth can you generalize? I mean, I thought of all sorts of other things, like going off to infinity, usually. And if you go off to infinity, you have a nicer structure out there. But then it didn't seem to me right, because twistor theory is supposed to be a theory that you could apply here. Why should we have to go off to infinity in order to understand what's going on here? Okay, maybe there is some remnant of what's going on at infinity still hanging around here, but how do you find that? And it was a long time before I sort of realized what you've got to do is somehow not have your space. And you have somehow got your holomorphic functions, but not the space. And I was puzzled by this, and I was so puzzled that I asked Michael Attier, it's rather inappropriate, some gathering, which happened to be in Buckingham Palace, but forget about that. and he said, well, you know, yeah, you can still find that if you've got your holomorphic functions, your prime ideals and so on. Well, I sort of knew that, but I didn't face up to it. But then he said, this is the key point, but that's not true if you have a non-commutative algebra. Wow, I thought. We do have a non-commutative algebra, but it's just not being used here. That is the commutation algebra. The z's and z bars do not commute. And it's, you see, this is always appealed to me in some ways, because we don't want z bars. We want everything to be holomorphic. D by dz is holomorphic. So if you think of your z bars all the time as being secretly d by dz's, you're still within the realm of complex analytic stuff. So can you do that? And the point really here is that you've got to face up to it and say, yes, indeed, the deformation has to be not of the twistor space, but of the non-commutative twistor algebra. So the idea is somehow you just think of the algebras and you patch them together. And it's a key point that the algebras, see, you think in quantum field theory of algebras, and you've got these operators, and then somewhere there's a vacuum space, and these things are supposed to be acting on the vacuum space. But the thing is, that doesn't work here, because you want to have something where the algebra is there, and it doesn't know a particular vacuum space. Roughly speaking, you've got something like, think of old-fashioned or standard quantum mechanics, where you have a system where you've got non-commuting operators. And then you say, well, we'd like to find a complete set of commuting operators. And that complete set of commuting operators give you your Hilbert space, roughly speaking, and this enables you to go ahead. But you might find another complete set. Now, the thing is here that in order for this to work, that changes as you go around. The algebra stays put, but as you go around, the things on which they would operate, there could be some freedom in that, but that freedom is exploited so that it's not consistent as you go all the way around. And that's the general idea here. That was the general idea for a long time, and it's taken quite a while to piece various things together. I'm still trying to piece them together. But let me give you, rather than piecing them together here, which I can't really do, I want to give you some of the ingredients. Now, actually, I should worry about the time. How long do I have? Is it a negative time yet? Or?
Not quite.
Not quite.
4 minutes, but
well, I'll see what I can do. Point number one: the space of light rays is naturally a symplectic manifold if you momentum scale the light rays. Now, this is well known. This is sort of PDX stuff, and you can do it with twistors as well. Okay. That is a symplectic manifold. A symplectic manifold if you momentum scale them. Now, there is a procedure known as geometric quantization. And I've got various slides which I should just flash at you, I think, because I don't want to talk about it much. Geometric quantization procedure. And the first thing you do is construct a circle bundle over your symplectic manifold. Well, what's nice here is that circle bundle's already there. So if you take, and this is the thing which only holds in the number of dimensions we have in space-time. One of the motivations behind twistor theory is that space-time is 3 + 1 dimensions, even though lots of theories require us to go up to higher dimensions. And I've always regarded 3 plus 1 as the deep thing which we have to explain, and have a formalism which really is geared to that is something positive in my view. And here you see a feature of that this circle bundle is already there. It's the spinor freedom that you have. Here you've got your flag plane pointing along the light ray, but it's also got this freedom which I mentioned before. And that is a circle bundle. And then you can talk about this connection which works perfectly well, and you can do it generally. I won't say too much about that. That's step number 1, an ingredient. Another ingredient you need is a thing called local twistor transport. This is conformally invariant notion, which tells you if you got any point in space-time, then you have naturally a twistor space associated with that point. You can move that around as a twistor propagation, which tells you how to move it around. If the space is conformally flat, it's integrable, so you get back to where you started. If it is not, you have a term from the conformal curvature, which gives you trouble. Now, but nevertheless, you can go up a light ray, and so it extends this twistor space, this flat space, twistor space, to the entire light ray. And therefore, you have a notion of a twistor space associated with a light ray. You can think of this as, roughly speaking, the tangent space to the thing one's trying to construct. But the light ray space sits in it, and it seems to be a natural thing. Another point is, I've said all that. Yeah, the other point I wanted to say is this. Now, you see, I was in Mexico, I think just last week, or was it 2 weeks ago? I can't remember now, but it was recently. And I was talking to a chap there, Ernesto Lupiccio, and he was telling me about non-commutative geometries. And you say, oh, yes, well, the simplest example is this one. And they say, oh, that's very interesting. It looks awfully twisterish. Maybe we can find that somewhere. And I had to give a talk on twistors the next day, or one couple of days. And it just dawned on me that the space he was describing is almost exactly this picture. You see, this is a fibration, the Hopf fibration of the 3-sphere. And you multiply that by a circle. And then you show how to get the simplest non-commutative geometry out of this space, which is naturally a complex manifold, and it's a non-projective space. It's not Kähler. But anyway, you have the circle because you've got the pi. Remember, the pi has a globally defined phase. Multiply this picture by this is the circle bundle over the 2-sphere. And then you have this space, which is called a toric variety, and then you're supposed to do things which give you a non-commutative algebra, which seems to me incredible, because here was this thing sitting all this time, and now we find a use for it. So roughly speaking, remember what this is. This is a picture of a twistor looked at in terms of the dual. Now, you see the dual was complex conjugates, but now you go to this holomorphic non-commutative geometry. And so the twistor now represents a certain substructure in the algebra. So the twistor is substructure in the algebra. Also, the points will be other kinds of substructures in the algebra. So when you get straight what this whole algebra looks like, in that you can find substructures which represent twistors, which represent the points in space-time. And those points, if you give it a Hermitian structure, those points in space-time are naturally real points, and there will be naturally real projective a real Lorentzian space-time. Moreover, suppose you want to satisfy the Einstein equations. And this is something which I'd known for some time, but hadn't seen a reason for it. We know that, well, standard Einstein theory without a cosmological constant is to say that the Ricci tensor vanishes. Now, what does the Ricci tensor vanishing? You see, if the Weyl curvature vanishes, that tells you something's integrable. It's conformally flat. But what is the Ricci tensor vanishing? What does that tell you something integrable? Well, I didn't know anything. Actually, I did. Because what it tells you is that in this local twistor theory, this thing, the infinity twistor, if is constant, if and only if Einstein's vacuum equations hold. And if it's a non-degenerate one, it's the Einstein equations with lambda, vacuum. If it's degenerate, then it's Einstein's equations with lambda equals 0. So that you see, that if you get everything else straight, Einstein's equations become a triviality. Of course, the rest of it is where all the complication lies. But the Einstein equation just simply saying you have an infinity twistor which is globally defined over the whole space. OK, that's the theory insofar as it goes. There are lots of details which I do know about, but most of them I don't know about. So it's a good thing I don't have to tell you about them. as stands, Palatial Twistor theory could not be a proposal for quantum gravity because, for a very simple reason, there is no role for the Planck length. So it's a formalism, quantumish formalism. You can probably do standard quantum theory in nice ways, but it's not quantum gravity, whatever that is. However, and this is something which I had actually thought about a long time ago, why don't you have a commutation relation between the z's? And I remember thinking about this way, way in the early days, and this is when I didn't think there was a cosmological constant. And if this thing is singular, then you can do a simple transformation and get rid of it. So I thought, oh, it's not interesting. But when this thing has a lambda in it, these things seem to be non-trivial. So now you have this set of commutation rules between the twistors and their complex conjugates, and this with the complex conjugate and the twistor. And it seems to me that some combination of all this gives a chance for some indication of how you might do quantum gravity of some sort. The Planck scale comes in because of the relationship between the constants coming in here and here. It's quite subtle how it all comes together. You also have a lambda in it, but you seem to have a big number, which you want. You want some number of the order of 10 to the 20 or something in order to get, you see, lambda is nothing like the Planck scale. You see, it's way on the other side. You've got a quantity which defines a huge length. In the other case, you've got something which defines a tiny length. And you've got something like 10 to the 120 or whatever it is between the two. And how do you make sense of that? Well, you need to feed a number in somewhere, which is at least something like 10 to the 20 probably. And then the 120 is maybe the 6th power of that. Well, you see 6-degree functions come in with dual twistors. Sorry, with the right-handed, with the googly thing. Anyway, this is only pure speculation, because I have no idea what this does for us. But it does seem to me that it's something worth exploring. Could it be that this does lead you to some kind of quantum gravity theory? It's very different from the approach that people tend to use when they think about non-commutative geometry applying at the Planck scale. They think of, say, maybe the position operators don't commute with each other, and so on. This is not doing that at all. It's doing something very different, and maybe it's somewhere fruitful to go. I don't know. It seems an interesting prospect to follow up. Thank you very much.
Are there any questions?
There's one.
Yes.
Oh, you got some? There.
Yeah, please.
How do you propose to generalize the nonlinear graviton?
Oh, that's exactly, sorry, I probably rushed through it too fast. But the nonlinear graviton construction, you take two patches of honest spaces, which are complex manifolds, and you glue them together, and then you look for the lines in that, the holomorphic lines, and they give you the points in the space. Now here, you're patching together the algebras. So you don't have the space, you just have the algebras. And that new algebra, you then look for, within that algebra, certain commuting subspaces, and those correspond to the points. So it's a straightforward generalization, because in the nonlinear graviton, you're saying you're looking only for patching together the algebras where you keep the z's among themselves, and you're looking for a very special type of algebra to algebra correspondence. Whereas here you're looking for a more general one which mixes up the z's and the z bars, but they're in the form of d by dz's. And so if you just keep to the z's, that's a sort of limited case, which is the old nonlinear graviton. If you're allowed to mix them up with the d by dz's, that's the general case. If you just had d by dz's, that would be the Googly problem.
So do you think that you get the negative one, the other helicity? So in the usual case, you have this complex functional deformation which are related to the, let's say, the self-dual solutions.
Yes. Well, that's
saying that in this case you would get the other ones?
Oh, certainly. I mean, that's natural because you can see certainly the complete dual ones are there, because that's just those particular transformations of the algebra which simply take functions of the derivatives, if you see what I mean. You just pretend that the z's were z bars, and now for z bars you write d by dz's. And if you're in the algebra of the d by dz's by themselves, it commutes. And so you have the old construction the other way around. So you certainly have the googlies in there, because I mean, there are problems about how you define locality and all sorts of issues about how you make this construction rigorous. And I don't know how to do that. But the general idea is symmetrical with respect to the right-handed and left-handed. So you can do the right-handed, and so therefore you can do the left-handed. But what is questionable at the moment is to what extent does it really do the ones in between, which involve both helicities together. But I think there is a pretty good chance that if one gets the rigor of it right, and we need something like an analog of the Kodara theorems. The Kodara told us that the deformations you get, you have a 4-parameter family of these things. So what you want to say here is that in a general deformation, these completely commuting subspaces, which are the analogs of the lines, form a 4-parameter family. And I need a theorem which says that. If that's not true, I'm in trouble. But that's the idea. So yes, certainly you get left-handed as well as right-handed, but do you get the ones which involve left and right? Oh, sure. No, that's a conjecture at the moment. But I would say it has a reasonable chance of being right. But these are guesses at this stage, I'm afraid.
All right, so I think maybe...
Oh, there was a question here? Did you?
Should I take more questions? Or...
Yeah,
yes?
sure.
A quick
Yeah.
question.
Very naive question.
Go ahead.
Do you think this formalism could relate to loop quantum gravity and spin networks?
I don't know. I mean, it would be interesting to see if it does. I mean, loop quantum gravity has a chance of being related to this because it has the right number of spatial dimensions. I would hate to think that it related to string ideas because string ideas, as they've gone, seem to depend on high dimension. Now, I think I'm quite happy about strings, but what I'm not so happy about is having to do all these extra spatial dimensions, whereas the loop quantum gravity theory is at least honest with regard to the number of dimensions. So it's quite possible there is a connection, but I certainly was not directly motivated. I mean, that would be an interesting question to see. Does one see a connection between this and what they're doing? Yeah.